The human body is a masterpiece of biological exclusion, a high-security fortress that has spent millions of years evolving to identify, attack, and expel anything that does not carry the specific molecular signature of self. Yet, at this very moment, millions of people are walking, eating, and breathing with substantial pieces of industrial-grade metal integrated directly into their skeletons. A tiny screw threaded into a jawbone to support a tooth, or a sophisticated sphere and socket replacing a degraded hip, represents a profound mechanical achievement. This is the realm of titanium, a silver-grey transition metal that possesses the unique ability to exist in a state of permanent biological truce with human tissue. While the immune system typically reacts to foreign objects with the aggressive intensity of a security force neutralizing an intruder, it treats titanium with a baffling level of indifference that eventually matures into a literal structural union. This phenomenon, where a non-living material becomes an inseparable part of a living organism, is not a result of the metal being friendly, but is a consequence of a specific, high-energy chemical barrier that characterizes the 22nd element. Understanding the hidden mechanics of the materials that define our physical boundaries is essential for a deeper appreciation of the technological age. Subscribing to the channel and contributing a perspective in the comments helps ensure that these detailed investigations into the engineering of our world continue to reach those who seek a sophisticated understanding of the elements. To understand the biological success of titanium, one must first analyze the standard response of the human body to a foreign intrusion. When a material like stainless steel or a splinter of wood enters the soft tissue, the body initiates a massive inflammatory cascade. Specialized white blood cells, known as macrophages, arrive at the site to inspect the object. They attempt to dissolve it using powerful enzymes and acids. If the object resists destruction, the body attempts to wall it off with a thick layer of fibrous scar tissue, effectively isolating the intruder from the rest of the biological system. In the case of most metals, this rejection is exacerbated by the release of metallic ions. Atoms of iron, nickel, or chromium slowly leak from the surface of the object into the surrounding fluid, reacting with proteins and triggering a persistent immune alarm. This is the primary reason why most metals eventually fail when used as long-term implants. They are either rejected by the immune system or the surrounding bone begins to recede, leading to a loss of mechanical stability. Titanium operates on an entirely different set of physical rules. Its biological invisibility is a direct result of its extreme reactivity with oxygen. This is a chemical paradox. Titanium is successful in the body because it is so reactive that it is never truly naked. The moment a piece of titanium is exposed to the atmosphere or the H2O-rich environment of the human body, it reacts instantly to form a passive oxide layer, primarily titanium dioxide, TiO2. This layer is a ceramic shield, only a few nanometers thick, but it is incredibly dense, stable, and insoluble. In engineering terms, this oxide layer acts as an absolute molecular seal. It prevents the internal titanium atoms from leaching into the body as ions, and it prevents the body's corrosive salts and proteins from reaching the metal. This TiO2 surface is so chemically inert that the body's security proteins simply find nothing to latch onto. The immune system does not "5" the titanium. It simply fails to notice it is there, treating the implant as a neutral, mineralized surface, similar to a natural bone. This neutrality leads to the most remarkable aspect of titanium's biography: osseointegration. This is a process where the living bone cells, called osteoblasts, do not merely tolerate the metal, but grow directly onto its surface, filling in the microscopic irregularities of the TiO2 layer. To explain this on the fingers, if you place a smooth glass marble in a box of wet sand and shake it, the sand will move around the marble, but it will never truly stick. If you replace that marble with a piece of titanium that has been etched to have a rough, porous surface, the quote 6, the bone cells, will crawl into the pits and valleys of the metal, creating a mechanical lock so powerful that the two materials effectively become one. When a dental implant is fully osseo-integrated, it is no longer a screw sitting in a hole. It is a structural extension of the jaw. The bone and the metal are bonded with such intensity that if an attempt were to be made to remove the implant, the bone would fracture before the bond at the metal surface would break. The engineering brilliance of titanium in the human body also involves a property known as the modulus of elasticity. This is a measure of how much a material stretches or deforms under a given load. Essentially, it's __7__. Most structural metals, such as steel or cobalt chrome alloys, are incredibly stiff, possessing a modulus that is many times higher than that of human bone. This creates a problem known as quote 8. Bone is a dynamic tissue. It follows Wolff's law, which states that bone grows and maintains its density in response to the physical loads placed upon it. If a hip replacement is made of a material that is too stiff, that metal carries all the weight of the person's stride, and the surrounding bone, __9__, because the bone is no longer being stressed, the body begins to reabsorb the calcium, causing the bone to thin and the implant to eventually loosen. Titanium, however, possesses a modulus of elasticity that is much closer to that of natural bone than any other industrial metal. It allows for a more natural distribution of weight, ensuring that the living bone continues to experience the mechanical signals it needs to remain dense and healthy. This combination of chemical ___, _10 ___ and mechanical ___, _11 ___ is what allows titanium to stay inside a person for 30 or 40 years without causing a single inflammatory flare-up. It is a material that has mastered the art of being an ___, _12 ___. It refuses to react, refuses to corrode, and refuses to change. And yet, through that very refusal, it becomes the most reliable partner the human body has ever had. The pinkish-red hue of a healthy gum line around a titanium dental post is a visual confirmation of a successful merger between the first minutes of the Big Bang, where the titanium was forged, and the complex, carbon-based life of the present. The extraction and processing of this metal, however, stand in stark contrast to its quiet biological life. Despite being the 9th most abundant element in the Earth's crust, titanium is notoriously difficult to produce in its pure metallic form. It is never found in nature as a shiny nugget. It is always locked in a tight embrace with oxygen in minerals like ilmenite and rutile. To liberate the metal, humans must use the Kroll process, an industrial ordeal that involves turning the ore into a gas, titanium tetrachloride, and then reacting it with molten magnesium at temperatures exceeding 500 degrees Fahrenheit. This must be done in a pressurized vessel filled with inert argon gas, because if even a trace of oxygen or nitrogen touches the hot titanium, the metal becomes brittle and useless. This high energy cost and the complexity of the __13___ manufacturing are what keep titanium expensive, ensuring that it remains a material reserved for the most critical of applications, where failure is not an option. When we consider the titanium screw in a dental implant, we are looking at a material that has survived the most extreme conditions imaginable. It was forged in the core collapse of a massive star, buried in the Earth's crust for billions of years, subjected to an industrial, quote, 1/4 of molten magnesium to be purified, and finally placed into the most corrosive environment of all, the human body. Once there, it enters a state of absolute stability. It does not react with the salts of our blood, it does not dissolve in the acids of our digestion, and it does not trigger the wrath of our immune system. It sits in the dark, silent and unyielding, providing the mechanical foundation for our lives, while remaining a total stranger to our biology. It is the ultimate quote 15 of the periodic table. A metal that has found a way to bridge the gap between the cold world of engineering and the warm, vulnerable world of human life, without compromising a single atom of its identity. This is the paradox of the titanium shell. It is the most foreign thing we can put inside ourselves, and yet it is the only thing our body truly forgets is a stranger. The genesis of titanium is a testament to the sheer, uncompromising violence of the early universe. A material forged not in the steady, predictable glow of a common star like the sun, but in the chaotic and terminal spasms of celestial giants. To find the origin of the 22nd element, one must look back to the final seconds of a star possessing at least 10 times the mass of the solar system's center. In these high-gravity environments, the stellar engine eventually reaches a thermodynamic limit where it can no longer produce energy through the fusion of lighter elements. When the star attempts to fuse iron, the process becomes endothermic. It consumes more energy than it releases, triggering an immediate and catastrophic gravitational collapse. The outer layers of the star, weighing trillions of tons, crash inward at nearly 25% of the speed of light, striking the ultra-dense core and rebounding in a supernova explosion. In that brief, blinding flash of energy, where temperatures exceed 3 billion degrees Fahrenheit, the pressure is so intense that nuclei are forced together in a process called nucleosynthesis. Titanium is a product of this cosmic forge, a high-energy residue of a star's death, scattered across the interstellar void as microscopic dust. This stellar shrapnel eventually became incorporated into the rotating nebula that formed the solar system, approximately 4.6 billion years ago. The presence of titanium on Earth is the result of this massive, primordial distribution of matter. However, the distribution of this metal within the planet itself is governed by a specific chemical preference known as lithophilia, or A_quote_16_. During the early molten phase of Earth's formation, the planet underwent a process of gravitational differentiation. Dense metals like iron and nickel sank toward the center to form the core, but titanium possessed a different set of priorities. Due to its atomic structure, specifically its 4 valence electrons, titanium has a powerful affinity for oxygen. Instead of dissolving into the liquid iron and sinking into the abyss of the core, titanium bonded with the lighter silicates and oxygen-rich minerals that floated to the top, forming the Earth's mantle and crust. This chemical behavior is why titanium is the 9th most abundant element in the Earth's crust, making up approximately 0.63% of the planet's outer shell. It is significantly more common than better-known metals like copper, lead, or tin. Yet, despite this overwhelming abundance, titanium remained a phantom in the history of human technology until the late 1700s. The paradox of titanium is that it is everywhere and nowhere at the same time. It exists in nearly every handful of common soil, every grain of beach sand, and every igneous rock. But it never exists as a pure metallic substance in nature. While a person might find a native nugget of gold or a vein of pure copper, the probability of finding a piece of metallic titanium in the wild is 0. The metal is a chemical hostage, locked in a permanent and incredibly powerful embrace with oxygen, forming minerals like ilmenite and rutile. The strength of this oxygen-titanium bond is one of the most significant hurdles in the history of material science. To understand why it took humanity thousands of years to see titanium, one must compare it to the extraction of iron. Iron ore can be reduced to metal by heating it with carbon in the form of charcoal. The carbon steals the oxygen from the iron, leaving behind the pure metal. But titanium's grip on oxygen is so fierce that carbon is an ineffective thief. At the temperatures found in a traditional forge, titanium would rather bond with both the oxygen and the carbon than exist in a pure state, resulting in a brittle, useless carbide. This chemical stubbornness is why the element was initially dismissed as a laboratory curiosity after its discovery in 1791 by the amateur geologist William Gregor. For over a century, the metal remains trapped in its mineral state, a hidden titan lurking within ordinary black sands and volcanic rocks. The geological concentration of titanium into mineable ore is a process that operates over millions of years through the relentless action of H2O and weather. In tropical and subtropical regions, the heavy rainfall and high temperatures leach away more soluble minerals, leaving behind concentrated deposits of titanium-rich sand. These are often found on the beaches of Australia, South Africa, and Canada. These heavy sands are a mixture of rutile, TiO2, and ilmenite, FeTiO3. The titanium atoms in these sands are the same ones that survived the supernova billions of years ago, having navigated the vacuum of space and the molten interior of the Earth to settle as dark, unassuming grains on a coastline. The effort required to move these atoms from their oxidized state into a refined metallic form is what defines the high economic and energetic price of titanium. The modern method of producing titanium, the Kroll process, is a masterpiece of industrial persistence that reflects the metal's difficult character. Developed in the 1940s, the process requires turning the titanium ore into a gas, titanium tetrachloride, and then reacting it with molten magnesium in a pressurized, argon-filled vessel at 1,500 degrees Fahrenheit. This must be done in a total vacuum, or an inert atmosphere, because if even a single molecule of oxygen or nitrogen touches the hot titanium, the metal will absorb it and become permanently brittle. To produce titanium is to conduct a war against the atmosphere itself. It is a process that requires a massive input of energy, roughly 16 times more than the production of steel, effectively freezing the electricity into the metallic structure. This is why titanium is often referred to as a frozen energy metal. The atomic architecture of titanium is what gives it its legendary engineering characteristics. With an atomic number of 22, it sits in a sweet spot on the periodic table. It is significantly lighter than iron, with a density of 4.5 grams per cubic centimeter, compared to steel's 7.8. Yet it possesses a tensile strength that rivals many high-grade alloys. This efficiency is a direct result of its hexagonal, close-packed crystal structure at room temperature. In this arrangement, the atoms are stacked like precisely organized oranges in a crate, creating a lattice that resists deformation and stress with remarkable effectiveness. When the metal is heated above 1,621 degrees Fahrenheit, it undergoes a phase transformation into a body-centered cubic structure, a shapeshift that allows engineers to tailor its properties for specific high-stress environments. The cosmic accident of titanium is thus a story of extreme abundance paired with extreme accessibility barriers. The universe produced a metal of divine strength and lightness, but it delivered it to Earth in a state of chemical camouflage. It is a material that requires the pinnacle of human energy management to unlock. We walk over it in the form of white titanium dioxide pigment used in common house paints and sunscreens, unaware that within those microscopic white particles lies a metal capable of defying the heat of a jet engine or the pressure of a deep-sea trench. Every gram of refined titanium is a testament to the fact that we have learned to overcome the billion-year-old chemical bonds formed in the cooling crust of the planet. The journey of titanium from the heart of a supernova to the crust of the Earth and finally into the hands of a human engineer is a narrative of persistence. It is a metal that refused to sink into the core, refused to be washed away by the rain, and refused to be liberated by the fire of the ancient smiths. Its history is a reminder that the most valuable resources in the universe are often those that hide in plain sight, protected by the very laws of chemistry that make them so useful. Titanium is a latecomer to human civilization, a material that had to wait for the age of electricity and vacuum chemistry to be revealed. Once unveiled, it proved to be an egoist of the highest order, unwilling to corrode, unwilling to fail, and possessing a strength-to-weight ratio that remains the benchmark for all other structural materials. The black sands of a distant beach are not just waste. They are a sleeping army of titans, a direct link to the explosive end of a distant star, waiting for the energy of a modern civilization to transform them into the invincible armor of the future. This cosmic heritage ensures that whenever titanium is used, whether in a spacecraft or a surgical tool, it carries with it the structural integrity of the stars themselves, a permanent and unyielding survivor of the universe's most violent events. The naming of the 22nd element was a rare departure from the dry, descriptive traditions of 18th century chemistry, reflecting a profound realization by the German chemist Martin Heinrich Klaproth. In 1795, upon isolating the element from the mineral rutile, Klaproth chose to bypass the standard practice of naming minerals after their physical appearance or geographic origin. Instead, he reached into the foundations of Greek mythology, naming the metal __28__ after the Titans, the primordial deities of immense strength and power who preceded the Olympian gods. This choice was not an exercise in poetic hyperbole, but an acknowledgement of the elemental __29__ he had encountered. Klaproth recognized that he was dealing with a substance that possessed a chemical grip so powerful it seemed to defy the standard tools of Enlightenment science. This __30__ nomenclature would eventually prove prophetic, as the history of titanium's transition from a laboratory curiosity to a strategic necessity became a high-stakes drama of industrial espionage and geopolitical irony that defined the coldest decades of the 20th century. For nearly 150 years after its naming, titanium remained a prisoner of its own atomic structure, a material that was theoretically understood but physically unreachable in industrial quantities. The metal's historical drama was defined by a prolonged state of chemical incarceration. While the 19th century saw the rapid expansion of the iron and aluminum industries, titanium resisted every attempt at mass production. It was not until the late 1930s and early 1940s that William Justin Kroll developed the process of using molten magnesium in a vacuum to strip the oxygen away from the titanium ore. This breakthrough occurred just as the global political landscape was fracturing into the adversarial blocks of the Cold War. Suddenly, the metal that Klaproth had named after ancient giants was identified as the only material capable of resolving the terminal limitations of high-speed aviation. By the late 1950s, the United States and the Soviet Union were engaged in an aerospace arms race, where the primary obstacle was no longer engine power, but the fundamental physics of heat. As an aircraft approaches speeds of Mach 3, 3 times the speed of sound, the air through which it moves ceases to behave like a fluid and begins to behave like a solid barrier. This is the phenomenon of aerodynamic heating. To explain this on the fingers, when a vehicle moves at such extreme velocities, it is not merely moving through the air, but is violently compressing the air molecules in its path. This compression generates a colossal amount of friction, turning the atmosphere into a microscopic abrasive, much like a piece of high-speed sandpaper. For an aircraft flying at 2,000 miles per hour, the outer skin can reach temperatures exceeding 600 degrees Fahrenheit, and in localized areas, 1,000 degrees Fahrenheit. In this thermal environment, the traditional materials of aviation, aluminium and magnesium, undergo a catastrophic loss of structural integrity. Aluminium, which defined the Second World War, begins to soften and lose its load-bearing capacity at approximately 350 degrees Fahrenheit. Using it for a Mach 3 aircraft would be equivalent to building a bridge out of wax. High-strength steel, while capable of withstanding the heat, is so dense that a plane built from it would be too heavy to take off with a functional fuel load. Titanium was the only solution to this thermodynamic, impossible choice. It possessed a melting point of 3,034 degrees Fahrenheit and maintained its strength at temperatures that would cause other metals to deform like plastic. It was the only material that could survive the heat barrier. This engineering necessity led to the creation of the Lockheed SR-71 Blackbird, the most sophisticated reconnaissance aircraft ever constructed. The Blackbird was designed to fly at the edge of space, at altitudes over 85,000 feet, and at speeds that allowed it to simply outrun any surface-to-air missile. However, the construction of this machine required a quantity of titanium that the United States did not possess within its own borders. At the time, the highest grade deposits of titanium ore, specifically ilmenite and rutile, were located in the vast territories of the Soviet Union. The primary technological symbol of American aerial supremacy was entirely dependent on the geological resources of its principal enemy. To resolve this paradox, the Central Intelligence Agency, CIA, orchestrated one of the most complex and clandestine logistical operations in the history of material procurement. The agency created a global network of shell companies, front organizations with innocuous names that appeared to be legitimate commercial entities in third world countries. These companies were used to place orders for Soviet titanium ore, ostensibly for the manufacturing of consumer products or industrial machinery. To explain this on the fingers, the United States was running a metallurgical shell game, using fake invoices and obscure shipping routes to move thousands of tons of Soviet minerals across the globe. The Soviet Union, desperate for hard currency and unaware of the ore's final destination, unknowingly provided the very armor for the plane that would spend the next 2 decades spying on its secret military installations. Every SR-71 that ever flew was, in a very real sense, a Soviet-American hybrid, a machine designed by California engineers and clad in the star ash of the Russian crust. The drama of titanium continued inside the manufacturing plants themselves, as the metal's unique properties required the invention of entirely new industrial techniques. Titanium is a material of memory and a material of intolerance. When Lockheed engineers began to work with the metal, they found that it was incredibly difficult to machine. It was so hard that standard steel drill bits would be destroyed after only a few holes. More significantly, the metal was hypersensitive to chemical contamination. During the early days of the Blackbird program, workers found that if they used ordinary city H2O to wash the titanium parts, the traces of chlorine in the water would cause the metal to crack and fail months later. The engineers had to switch to distilled H2O and develop specialized tool bits made of expensive tungsten carbide. Furthermore, the thermal expansion of titanium at Mach 3 was so extreme that the plane could not be built with traditional tight-fitting panels. Because the metal would expand by several inches as it heated up to 600 degrees Fahrenheit in flight, the SR-71 was designed with loose joints. On the ground, at a standard temperature of 70 degrees Fahrenheit, the fuel tanks actually leaked onto the runway because the panels did not yet fit together. The plane was only whole and sealed when it was flying at 3 times the speed of sound, heated by the friction of the atmosphere into its final, intended shape. This was the ultimate engineering of the egoist metal, a machine that only became perfect when it was subjected to the most hostile conditions possible. This era of titanium's history was a period of high-energy exclusivity. For decades, the metal was the secret ingredient of the military-industrial complex, a substance that was too expensive and too difficult for anything other than the most critical national security projects. It was a material that lived in the world of high-altitude reconnaissance and nuclear-powered submarines. The historical drama of titanium is the story of how a material that Klaproth named after the giants of mythology lived up to its name by becoming the cornerstone of the most advanced technology of the Cold War. It was the metal that turned the Iron Curtain into a titanium screen, a substance that forced enemies to cooperate through the hidden channels of the global market. Eventually, as the Kroll process became more refined and the secrets of titanium manufacturing were disseminated, the metal began to transition from the world of spy planes to the world of civil engineering and medicine. The Blackbird was retired, but the metallurgical lessons learned during its construction allowed for the creation of the medical implants and high-performance vehicles of the modern era. The drama of the Soviet-American plane remains a testament to the fact that the most advanced tools of human civilization are often built upon the most unlikely and clandestine foundations. Titanium was the metal that bridged the divide between superpowers, providing the physical strength to explore the edges of our atmosphere and the geopolitical flexibility to survive the most dangerous decades of the 20th century. It remains the invincible egoist, a material that demanded and received the total attention of the world's most powerful nations, proving that when the goal is the absolute mastery of speed and heat, the metal of the gods is the only material that can be trusted. The modern industrial landscape is defined by a relentless search for efficiency, a pursuit that has pushed the 22nd element out of the clandestine world of military secrets and into the palm of the average consumer's hand. Today, titanium functions as the invisible backbone of high-performance engineering, providing a combination of physical characteristics that no other material can replicate. The most immediate manifestation of this is observed in the evolution of flagship consumer electronics. When a modern smartphone feels surprisingly light despite its large screen and dense internal components, it is a result of a transition from stainless steel to titanium alloys for the external frame. This choice is governed by the metal's superior strength-to-weight ratio, which is arguably the best of any structural metal found in nature. To explain this on the fingers, if an engineer were to build two identical metal cages, one of steel and one of titanium, the titanium cage would possess the same structural rigidity while weighing approximately 45% less. This weight reduction is not merely a luxury. It is a mechanical necessity in a world where devices are becoming more complex, requiring more internal space for batteries and processors without becoming cumbersome to the human hand. The structural integrity of titanium is rooted in its atomic architecture, specifically the hexagonal close-packed lattice that defines its crystalline structure at a standard temperature of 70 degrees Fahrenheit. In this arrangement, the atoms are organized in a way that minimizes wasted space and maximizes the number of chemical bonds between neighbors. This creates a material that is incredibly resistant to deformation. While aluminium is light, it is relatively soft and prone to bending under stress. Steel is strong but heavy and susceptible to the corrosive influence of fire and oxygen. Titanium occupies the Goldilocks zone of material science, offering the durability of steel with a density that is significantly closer to that of aluminium. This allows it to act as a premium structural skeleton for devices that must survive the daily rigors of drops, pressure, and environmental exposure. However, the role of titanium in the modern era extends far beyond the aesthetics of a smartphone frame. It is the fundamental material that allows for the existence of the high-bypass turbofan engines that power global aviation. Inside a modern jet engine, the conditions are a literal thermodynamic hell. The air is compressed to pressures exceeding 600 pounds per square inch and heated to temperatures that can reach 1,000 degrees Fahrenheit, even before the fuel is ignited. In the front sections of the engine, the fan and the compressor, the blades must spin at over 10,000 revolutions per minute. At these speeds, the centrifugal force acting on each blade is equivalent to hanging a heavy freight locomotive from its tip. Any ordinary metal would undergo a process called creep, where the material slowly stretches like a piece of warm taffy until it strikes the engine casing, leading to a catastrophic failure. Titanium is the only material that can withstand these immense forces while resisting the heat and maintaining a light enough mass to allow the engine to spin efficiently. Without the titanium compressor blades, the fuel efficiency of modern flight would collapse, making international travel an expensive rarity rather than a daily reality. The deep-sea frontier represents another environment where titanium acts as the only viable engine of exploration. The weight of the world's oceans creates pressures at the bottom of the Mariana Trench that exceed 16,000 pounds per square inch. This is equivalent to having an adult elephant stand on every square inch of a vessel's surface. For most metals, this pressure is not the only enemy. The chemical composition of seawater acts as a powerful electrolyte, triggering rapid galvanic corrosion that eats through steel and aluminium with relentless speed. Titanium, as previously discussed, possesses a noble ego. It forms an oxide layer that is so stable and self-healing that it is virtually immune to the corrosive effects of salt. In the deep-sea environment, titanium allows for the construction of pressure hulls that are thin enough to be buoyant, yet strong enough to resist the crushing weight of the abyss. It is the metal that turned the deepest parts of the planet from an unreachable void into a laboratory for human discovery. In the realm of space exploration, titanium is the primary tool for overcoming the gravity tax of the Earth. Launching a kilogram of material into orbit requires an enormous expenditure of energy and fuel. Every gram of excess weight in a spacecraft is a gram of scientific equipment or life support that cannot be carried. This is why the Mars rovers, such as Perseverance and Curiosity, are essentially titanium masterpieces. From the landing struts that must absorb the shock of touchdown to the internal chassis that holds the radioactive power source, titanium is the material of choice. It can withstand the extreme cold of the Martian night, which can drop to -195 degrees Fahrenheit, without becoming brittle, a flaw that plagues many types of steel. Furthermore, its low coefficient of thermal expansion ensures that the delicate optical instruments and sensors remain in perfect alignment as the temperature fluctuates across hundreds of degrees. The chemical industry also relies on titanium to handle the most aggressive substances produced by human ingenuity. In plants that manufacture sulfuric acid, H2SO4, or chlorine, the pipes and vats are subjected to environments that would dissolve a standard iron pipe in a matter of hours. Titanium's ability to remain inert in the presence of these molecular sores makes it the essential infrastructure for modern chemistry. It allows for the safe containment and processing of the materials that eventually become our medicines, our fertilizers, and our plastics. It is the invulnerable egoist that stands between us and the corrosive potential of our own industrial creations. The high-tech world of professional sports and high-end automotive engineering also utilizes titanium as a performance multiplier. In the world of Formula One racing or high-altitude mountain climbing, the reduction of weight is directly correlated to speed and survival. Titanium valves in a racing engine can open and close thousands of times per second because their low mass reduces the inertia the engine must overcome. Titanium bicycle frames and camping equipment provide a level of durability that survives decades of use without the threat of rust or structural fatigue. It is a material that has become synonymous with the limit cases of human endeavor, The tools we use when we want to go faster, deeper, or higher than our biological limitations should allow. To explain the hidden work of titanium on the fingers, it is the metal of peace of mind. When we fly across an ocean, we are trusting our lives to the fact that the titanium blades in the engines will not stretch. When a doctor replaces a joint, they are trusting that the titanium will not corrode. When a scientist sends a probe to another planet, they are trusting that the titanium will not shatter in the cold. It is a material that performs its duty with a quiet, unyielding consistency, requiring no maintenance and offering no compromises. The egoism of the metal, its refusal to interact with the environment, is its greatest gift to modern civilization. Despite its ubiquity in high-end products, the engineering of titanium remains a specialized art form. Because the metal is so strong and so resistant to heat, it cannot be shaped using traditional methods. It must be machined with specialized tools, often in a vacuum or under a stream of inert gas to prevent it from catching oxygen and becoming ruined. The advent of 3D printing with titanium powder, a process called selective laser melting, is the newest chapter in this story. It allows for the creation of complex, organic shapes that were previously impossible to manufacture, such as lattice structures that mimic the internal architecture of human bone. This technology is turning titanium into a living metal, where the design is limited only by the imagination of the engineer rather than the constraints of the furnace. The 20th century was the era of steel and oil, but the 21st century is increasingly becoming the era of titanium and silicon. It is the material that has allowed us to bridge the gap between the organic and the mechanical, between the surface of the Earth and the vacuum of space, and between the crushing pressure of the sea and the delicate signals of our digital networks. Titanium is not just a metal. It is a physical guarantee of stability in an unpredictable world. It is the substance that proves that we can build a world that does not rust, does not fail, and does not succumb to the passage of time. As we continue to push the boundaries of what is possible, the 22nd element will remain our most trusted and unyielding partner. The egoist in armor that makes the impossible routine. The ultimate legacy of human civilization on the geological record will be defined not by the organic remnants of its biological life or the crumbling ruins of its concrete cities, but by the chemical persistence of its most advanced materials. In the deep history of the Earth, stretching across millions of years, most objects of human construction are destined to undergo a process of total environmental reconciliation. Steel, as previously noted, returns to the state of iron oxide or rust within a few centuries. Plastics are eventually degraded by ultraviolet radiation and specialized microbial activity. Concrete is pulverized by the mechanical cycles of freezing and thawing H2O. However, the 22nd element, titanium, occupies a position of total thermodynamic immunity in the face of these entropic forces. Because it is chemically incapable of standard corrosion and physically resistant to the passage of eons, titanium is the primary candidate for the role of the final artifact, the material that will serve as a permanent, untarnished witness to the human era long after the atmosphere and the oceans have reclaimed everything else. The mechanism of this extraordinary longevity is rooted in the extreme stability of the titanium dioxide, TiO2, layer that encapsulates every titanium object. This is a passive film that functions as a molecular seal of near absolute efficiency. To explain this on the fingers, while iron reacts with oxygen to form a porous, flaky layer that allows the destruction to penetrate deeper into the metal, titanium reacts with oxygen to form a ceramic armor that is as hard as sapphire. This layer is only about 10 nanometers thick, yet it possesses a density that is impermeable to H2O, oxygen, and even the most aggressive corrosive salts found in the deep ocean. If this armor is scratched or physically breached, the underlying titanium does not begin to rot. Instead, the surrounding oxygen in the air, or H2O, reacts with the exposed metal to regrow the shield in a matter of nanoseconds. This is a self-healing capability that operates with the mechanical certainty of a physical law. It ensures that the structural integrity of the metal is never compromised, allowing it to remain in a state of high-energy, metallic perfection for timescales that dwarf the entire duration of human history. In the future archaeological record of the planet, titanium will appear as a techno-fossil of unprecedented clarity. When the soft tissues of the human body have decayed and the natural minerals of the bones have been replaced by stone through the process of permineralization, the titanium implants within those skeletons will remain unchanged. A titanium hip joint or a dental post will exist within a fossilized skeleton as a pristine silver-gray anomaly. Future observers or geological processes will encounter a material that does not belong to the natural mineralogy of the Earth's surface in its metallic form. These artifacts will remain as clear and functional as the day they were manufactured, providing a permanent chemical autograph of a species that mastered the energy required to reverse the chemical state of the crust. Titanium is the only material that allows the human form to be etched into the geological record with a degree of permanence that survives the grinding pressure of tectonic plates and the corrosive chemistry of the deep Earth. This persistence extends beyond the boundaries of the Earth and into the vacuum of the solar system. The space age has left a trail of titanium artifacts across the Moon, Mars, and the outer planets. Because there is no H2O or oxygen in the vacuum of space to facilitate chemical decay, and because titanium is exceptionally resistant to the degrading effects of solar radiation, these objects are essentially immortal. On the lunar surface, the landing legs of the Apollo lunar modules and the frames of the lunar rovers will remain in a state of near-perfect preservation for millions of years. They are immune to the cold welding that can cause other metals to fuse together in a vacuum, and are strong enough to withstand the relentless bombardment of micrometeoroids. Each of these machines is a concentrated piece of the Earth's crust, refined by the Kroll process and hurled into the void, where it serves as a silent, non-corroding sentinel. To any future civilization exploring the solar system, these titanium structures will represent the first reaching out of a terrestrial species, providing a durable proof of technological achievement that does not fade with the passage of time. The egoism of titanium, its refusal to participate in the chemical cycles of its environment, is what makes it the ultimate archive of human ingenuity. In the deep ocean, where the pressure reaches 16,000 pounds per square inch, and the salt water acts as a powerful solvent for most metals, titanium remains unaffected. A titanium pressure hull from a deep-sea submersible, if lost on the abyssal plain, would not dissolve or pit over thousands of years. It would simply sit in the dark, its surface protected by its invisible oxide skin, waiting for a geological event to bury it or for a future explorer to find it. This resistance to pitting corrosion, a process where localized chemical attacks create deep holes in a metal surface, is what separates titanium from even the highest grades of stainless steel. It is a material that resists the molecular sores of the environment with an indifference that is almost total. The long-term movement of titanium through the Earth's crust is a process of extreme geological patience. Because titanium is lithophilic and bonds so tightly to oxygen, it does not easily migrate or dissolve into groundwater. Once it is buried in a sedimentary layer, it stays there. Over tens of millions of years, as the layers of the Earth are folded and pushed deep into the mantle through the process of subduction, the titanium artifacts of the human era will finally be subjected to temperatures and pressures that can overcome their stability. In the intense heat of the mantle, which can exceed 2,000 degrees Fahrenheit, the chemical bonds of the titanium dioxide will eventually be broken, and the metal will be reintegrated into the molten silicate soup of the Earth's interior. This is the only death possible for the element, a return to the volcanic furnace from which it was originally released by human industry. Until that moment of geological reconciliation, titanium remains the most Chesney material in the human inventory. It does not pretend to be biological, yet it allows itself to be woven into our bones. It does not pretend to be light, yet it allows us to fly at 3 times the speed of sound. It does not seek the attention of the environment, yet it survives every attack the environment can mount. To explain its role in the ultimate future on the fingers, it is the black box of the human species. If every book were burned, every hard drive erased, and every city ground into sand, the titanium screws in our skeletons and the titanium hulls on the moon would still be there. They are the only objects that can carry the story of our engineering into the depths of time without loss of data. The 22nd element is a material that has survived the transition from a stellar catastrophe to a hidden mineral, and then to a strategic secret of the Cold War. It has moved from the spy planes of the CIA to the dental clinics of the suburbs, maintaining the same uncompromising physical integrity throughout every stage of its biography. It is a metal that lives in a state of high-energy exile, having been forcibly separated from oxygen by a massive expenditure of electricity. Yet it uses that very energy to create a permanent shield that prevents it from ever being destroyed. It is the invincible egoist, because it exists for its own structural stability, refusing to react, refusing to fail, and refusing to succumb to the passage of eons. When the sun eventually enters its red giant phase in 5 billion years, and the Earth is consumed by the expanding solar atmosphere, the titanium that was once part of our world will be returned to the stellar environment. The atoms will be vaporized and scattered back into the interstellar medium, joining the primordial clouds of gas and dust from which new solar systems are born. Because titanium is a stable element, those same atoms that once held a human tooth or formed the wing of a blackbird will continue to exist as solitary, indestructible particles. They may eventually be drawn into the gravity of a new star to be forged again in a new supernova, continuing a cycle of existence that spans the entire life of the universe. Titanium is the element that reminds us that the quest for permanence is not found in the soft tissues of life, but in the unyielding lattices of the stars. It is the metal of the gods, the final artifact of the humans, and the most durable monument to the moment when a biological species learned to shape the matter of the universe into an invincible armor that time itself could not break. Every piece of titanium is a fragment of the ultimate future, a silver-grey promise that something of our ingenuity will remain as a polished and perfect witness at the end of the world.